All right, grade 11 physics. Here we go. I'm going to go through the chapter 6 work and energy notes. I'm just going to hit the highlights from box to box until I get to the end, just to give you a little bit of extra insight and hopefully clarify a few things that are extra confusing. But basically, this chapter is not nearly as bad as it looks at first. I think by the time I get to do some examples, things will start to come together. So if you're initially confused, don't worry about it. It's not that bad. And if you have any questions, you can definitely take advantage of that shared doc that Mr. Dawson and I made in Google Docs. Post your questions in there, and Mr. Dawson and I will do our best to answer them. And of course, you can all benefit from everybody else's questions being a shared doc. So don't hesitate to take advantage of that document. Okay, so let's go through this. Chapter 6, Work and Energy. In the first box, I just give you a quick bit of advice here. It is really worth your effort to memorize just these three cos values. The cosine of 0 degrees is positive 1, cosine of 90 degrees is 0, and the cosine of 180 degrees is negative 1. Those three values in particular show up a lot in problems, and it's kind of nice if you just intuitively know them. If any other angle shows up, feel free to grab a calculator, but preferably you won't have to look those three up. Especially these two, because the sine, as we're going to find out very soon, has important meaning in this chapter. The cos of 0 is positive. And by the way, the cos of anything between 0 degrees and 90 degrees is positive. And the cos of anything between 90 degrees and 180 degrees is negative. Kind of nice to know these things. All right, so I introduced the concept of work and basically say that it's the act of a force through a distance, with the equation for work being this. Work is equal to force times distance times the cosine of the angle beta, where beta is the angle between the direction of the force and the direction of the motion. As we're going to see soon, any force that acts through a distance can be thought of as doing work. All right, so work has the unit of the joule, J, where joule is basically just a shortcut for Newton multiplied by meter. And you can actually see that in the work equation here. If you take force in newtons and multiply it by a distance in meters, you literally have a value of Newton times meters, but we give that the special name of the joule. All right. Let's see here. What else do we have? Skipping through. I really do encourage you to read through these notes carefully. But like I said, I'm just trying to hit the highlights here, especially box to box, because I try to use these boxes to summarize things. Okay, not quite a box in the usual sense here, but maybe worth talking about. Energy is something for which there's a lot of different forms. This list gives you a list of a few forms of energy. For grade 11 physics, we're going to be focusing on really just these first two, kinetic energy and gravitational potential energy. The other ones are worth being aware of, but we're not going to be focusing on them in 30S physics. Okay, so kinetic energy is the energy of mass in motion. If you have mass m and it's moving with speed v, then it has kinetic energy. And of course, an object that's not moving, which is to say its speed is 0, does not have kinetic energy. But that's an important equation, 1/2 mv squared. Okay, gravitational potential energy, by comparison, is the energy that we associate with a mass being high up in a place that there's gravity. So the equation for it kind of brings that all together. U is the symbol that we use for potential energy, and no, that's not an obvious choice, but get used to it. U is a pretty standard letter used in physics for potential energy. You might be tempted to use something like a P for potential energy. Turns out that that's a problem because we're going to be using P for power very soon. So it's a weird choice of letter, but it's a letter that we're going to use often enough that it soon won't seem like a weird choice at all. So UG is gravitational potential energy, and it's the product of mass times the gravitational field, 9.8 near Earth's surface, times the height of the object above some level that you're measuring from. I go through this in quite a bit of depth here, but in a most typical kind of a situation, there's an obvious measuring point, such as the ground or the floor, or the lowest point an object moves. If an object is moving up and down, we'll often just use the lowest point that it reaches as the point that we're going to measure height from. All right. Let's see what else we have here. Okay, so mechanical energy and its conservation, basically summarized in a box that's coming up here. Basically, energy is something that is always conserved. You've probably heard of this before, maybe in your chemistry course or even earlier science courses. When we say that something is conserved, we really just mean that we don't know of any way to create it. We don't know of any way to destroy it. Energy is just out there. If you want to go get energy, you can get it. If you want to lose track of it, you can lose track of it. If you want to convert it from one form to a different form, these are all possibilities, but energy is essentially forever. We can only lose track of it, and we can only go get some, but we can't make it or lose it. Okay, now, this is probably one of the most confusing parts of the chapter, this idea of non-conservative forces. For the 30S physics, I'm going to say that this is probably something that you don't need to worry about too much. I think I can simplify this as far as 30S physics goes. I'm just going to say that non-conservative forces are all forces that we've seen, all forces seen in 30S physics, with only one exception. And that one exception is the force of gravity. This is one of those areas that the AP Physics honestly goes quite a bit more in depth than the 30S, 40S program goes. So I wrote these notes originally for my AP course, so don't get too hung up on this section. You can honestly get away with thinking of gravity as a special force. We're going to keep track of gravity in this chapter through the idea of potential energy, as we just saw, mgh. Every other force we're going to keep track of in a different way, through literally the concept of work. So non-conservative forces, don't get too worried about all of this stuff here. Yeah, I think that's probably safe to say for 30S physics. Okay, now just a quick little aside here. This is just a notation thing here. I am going to be switching from I and F for initial final in this chapter, and if we get into the momentum in the next chapter, I'm going to do that there too. Instead of using I's and F's for initial and final, I'm going to use a prime notation. So just think of it as something like this. Before I said V initial, I'm now in this chapter going to say V for a starting value. And instead of something like a V final, I'm instead going to say V prime. They mean the exact same thing. The only reason I'm switching notation is because in this chapter and the next chapter in particular, the subscript space can get very, very, very busy. For example, think of something like this, and really I'm thinking of in the next chapter this is more likely to show up, but nonetheless, just to show you what I mean, imagine if I were to say something like the velocity of object number 1 in the x component initially. I mean, if I say it, you can make sense of that. That's the velocity of object number 1, x component initially. But that just looks too much for my preference, at least. So rather than saying something like that, I would prefer to say the velocity of object number 1 in the x. And it would be understood that that was the initial value. Instead of saying the velocity of object number 1 in the x final, it is so much nicer to say the velocity of object number 1 in the x prime. Means the same thing, but let's not write it this way. Okay, so get used to those primes. Prime is just a really nice way of saying effectively the same thing as final. Okay, conservation of energy. So this is an equation that is very, very, very useful. And in fact, in 30S physics, you're only going to see the start of how useful this equation is. It will continue to be exceptionally useful in 40S physics, should you choose to take that course. So let's really make sense of this equation. The m's in both cases stand for mechanical energy. And from a 30S physics point of view, you can think of mechanical energy as being basically the total of all of the energy. We're only considering mechanical forms of energy, so it's not exactly right, but I think it's correct enough for 30S physics. In fact, I read this equation, especially the 30S way, is effectively the total energy. That you end up with as being the total energy that you started with, and there is a possibility of gaining energy or losing energy along the way. And it turns out that that's what work also can be thought of it I think of work as literally two things at the same time. Work is the act of a force through a distance, as we talked about in the previous equation. But work, especially this non-conservative work, is also the act of giving. I'm going to say giving if that net work is positive, or removing if the net work is negative energy. So yeah, you can think of work as two things at the same time. Force through a distance, but it's also the act of giving or removing energy. So what this equation is really saying is the energy that you end up with is equal to the energy that you started with, allowing for the possibility of an energy transfer through the process of work. Positive work gives energy, so you'll end up with more energy than you started with, and negative work is removing energy, so if the net work was negative, you could end up with less than you started with. Hopefully you're going to spend some time with these examples because I really try to give a few examples that make sense of this. But I'm going to skip over these right now. I'm going to do a couple of, I'll do the end chapter questions to try to clarify some of these things. So I'm just going to skip ahead all the way. Let's see, skipping. Oh yeah, power. Okay, so the last thing in this chapter that we're introducing as a new idea is power. Power is basically a measure of how quickly work is getting done, or more generically, how quickly energy is being transferred. The unit for power is a unit that you're almost certainly familiar with just from outside of physics because it's used quite a lot. The watt, symbolized as capital W, is the symbol for, the capital W is the symbol for the watt. And a watt is just a shortcut unit for joule per second. In fact, it's kind of worth remembering these things. Joule, oh, that's the wrong pen. Let's see, use that one. A joule, just to remind you, I think I said it earlier, is a Newton meter. And now I'm saying a watt is a joule per second. So if you hear something like a 60 watt light bulb, all that really means is that that light bulb is transferring energy at a rate of 60 watts, which means 60 joules per second. And that's literally what a light bulb does from an energy point of view. It takes an energy from one form, electrical, and it puts out energy of a different form. In a case of a light bulb, that's going to be partly light and also partly thermal energy. But 60 watts means 60 joules per second. So if you compare that to something like a 20 watt light bulb, that would be using energy much less quickly. Okay, so the two equations for power, and again, from a 30S perspective, I think we'll be using power less often in this unit, but it does tend to show up a lot more, especially in the electricity unit of 40S physics. But nonetheless, here's an introduction to power. You can think of it as the rate at which work gets done, so work divided by time. And this is really just a direct outcome of that work equation. In fact, I'll show this real quickly here. Using this equation, work is nothing more than force times distance. I'm going to assume that we have a beautiful cosine of 0 degrees, which is positive 1, so I'm not going to write it right now. But if you take force times distance, cos of 0 degrees, and divide that by time, you can actually see speed hiding in this equation. Distance over time is speed. So these two equations actually say the exact same thing, and it's true. We're assuming the ideal case of a 0 degree angle. We're assuming that this force F is pushing in the direction of this motion. A bit of a simplification, but it's one that's usually safe. Okay, a couple of examples, skipping ahead. Okay, so I wrote this up just before I started recording. Let me just give you a summary of the important equations in this chapter, and then I'm going to go over those 5 questions that appear at the end of the notes. Okay, so here's the summary. There aren't that many new equations in this chapter. The equations are work equal to force times distance times the cosine of the angle. Mentioned that earlier. It's worth pointing out that in this chapter, everything that's new is a scalar quantity. So do realize that work is a scalar. It doesn't have any direction. That doesn't mean that it can only be positive, by the way. Work can be positive, it can be negative, but that's not about direction. It's actually about giving or removing energy, as I mentioned not long ago. In this equation, force and distance are always positive. Always positive, because we're really considering force, the magnitude, how much force is there, and distance is literally the length of the path taken. It's not displacement. So they're always, always, always positive. That means that the sign of work, the question of whether it's positive or negative, is going to come exclusively from that angle beta, as I talked about before. And that's why I started this with that quick reminder of the cosine of those three special angles in particular. If we have a 0 degree angle, that's going to be +1, meaning that the work is positive. If the angle beta is 90 degrees, cos of 90 degrees is 0, any force that is perpendicular to the motion, a beta of 90 degrees, does 0 work. And if beta is 180 degrees, which is to say that the force is opposite of the motion, then it's true the work would be negative. And that's the removal of energy. Okay, next equation. This is a relatively simple one. Kinetic energy is the energy of mass in motion. So if you have mass m moving at speed v, you have kinetic energy. And clearly, mass is always positive. Speed itself is always positive, but even if it wasn't, that square would have enforced a positive. Kinetic energy is a special form of energy in that it cannot be negative. That's not a rule for other forms of energy. It's not a general rule. So think of that as a special feature of kinetic energy. Kinetic energy can be 0 if an object is stationary. It can be positive if an object's moving, but there's no third possibility. Kinetic energy can only be positive or 0. In fact, here I'll just kind of make a mention of that. Kinetic energy can only ever be greater than or equal to 0, which is to say it can never be negative. Not so for gravitational potential energy. Gravitational potential energy is mgh. And again, it's worth pointing out that in this equation, m and g are always positive. Okay, positive. And that's actually in contrast. There we go. That's actually in contrast with how we've used g sometimes in the past when we've worked with vector equations. And that is the difference. This is not a vector equation. This is a scalar equation. So m is the mass, certainly always positive. G is the gravitational field, and this is why I wrote the word strength in here. It cannot be negative. If you're in a place of no gravity, G is 0. If you're in a place, near Earth's surface, G is positive 9.8. And if you're somewhere else, it could be a different value, but that value will always be positive. This is not about up and down at this point. So just remember that. H, however, can be positive or negative. H is the height above, and I'm going to put above in quotation marks because that's the generic form of it, above a, I'm going to call it a reference height, because it is also the case that H can be less than 0 if you are looking at a point below the reference level. Yeah. So if we think of the ground as the reference height, then any point above the ground is a positive height, and that would correspond with a positive potential energy. Now imagine that you dig a hole into the ground, and at the bottom of that hole is literally below what we've been calling ground level. So if you're at the bottom of that hole, you'd be at a height that would be considered negative in this equation. And if you put an object in the bottom of that hole, it would literally have negative potential energy, a consequence of that negative H. And that's correct. Okay, next equation is, there we go, the mechanical energy. So this is just the concept of what mechanical energy means. It's the kinetic energy plus the potential energy. So again, from a 30S point of view, you can think of that as the total of all energy, at least of the types that we're considering. AP physics and even 40S physics can expand upon that, but I'm going to keep it just to that for 30S physics. It's essentially the total energy. And then finally we have this, which is what I would call a statement of the law of conservation of mechanical energy, at least. The mechanical energy that you end up with is equal to the mechanical energy that you started with, allowing for the possibility that energy has come in or gone out. So it's conserved, but that's not to say that we can't acquire some or transfer some out to somewhere else. And work is how we do that. All right, I forgot to write my power equations in here, so I can just slip that in here. Power is the rate at which work gets done, so work divided by time. I'm going to slip a little delta in here. It's the notation I prefer to use now. I didn't update my old notes. And it can also be written as power equal to force times speed, which actually assumes that it's in the preferred direction. A more general form of this, you could actually slip in the cos of beta. So if I want to, I can now think of these as slightly updated forms of the equations that appeared in my notes, but I don't think it'll be a consequence for 30S physics. Nonetheless, better form here. Okay, now, let me switch over. I'm going to do this, because I'd like to go over those 5 examples that appeared at the end of the notes, and I already copied and pasted them into my document here. So these are the same 5 problems, but let me go through these carefully to make sense of them. Okay, number 1. The question was, how much work is needed to get a 5-gram bullet moving at a speed of 300 meters per second? Okay, let's just use our general problem solving for this. I'm going to list off the information that was given, identify the unknown, and so on. Okay, so I was told that it was a mass of 5 grams. Of course, the SI unit is the kilograms, so a quick conversion into kilograms is 0.005 kilograms. The speed of the bullet, okay, now, again, I have to read into this a little bit. Presumably, before the bullet was fired, it was stationary, so not explicitly written in there, but I think a safe assumption, the speed was 0. But once the bullet has been fired, it's now moving at a speed of 300 meters per second. And you can see how I'm using that prime notation. The speed v without the prime, okay, so the absence of the prime here, if I kind of highlight that, the absence of the prime is basically saying initial, and the prime itself is indicating final. So there was a before and an after. All right, so the question is, how much work do we have to do? And I'm kind of generalizing that into that net work done by non-conservative forces. So I'm not really worried about what is doing that work. I'm just saying, in total, this is what's going to happen. Okay, so I'm going to use my general purpose equation of law of conservation of mechanical energy. The energy you end with is equal to the energy you started with, allowing for the work to change that. And in this case, of course, there is work that's changing that. There's going to be a force acting on our bullet over a distance. In the firing of an actual gun, that would come from the gas pressure behind the bullet, resulting from the explosion of the gunpowder. Okay. Mechanical energy prime is nothing more than the sum of the kinetic energy and gravitational potential energy. Ignore the fact that it's crossed out for just a moment. On the right side of the equation, we have the mechanical energy that we started with, K plus U gravity. And this is going to be a very kind of a familiar form that we're going to be doing. I'd like to write out the general form and then expand upon it with the types of energy that are involved. In our case, is kinetic energy and gravitational potential energy. But then I'd like to simplify the equation by figuring out what, if anything, I can just cross out. And I can cross things out if they are either equal to 0. So in this case, the kinetic energy was 0 because it was initially not moving. And if it's not moving, it has no kinetic energy at that point. Honestly, I don't know what the height of that bullet is. I don't know if the bullet was held at ground level or above ground level or somehow below ground level. And it doesn't really matter because I'm reading into this that we're only considering the firing of the bullet. We're not looking at the flight of the bullet. Like projectile motion is really not a part of this. So whatever height it was, I don't know. But it didn't change that height in just the act of firing the gun is I think, a reasonable assumption to make here without anything more specific being told to me. So whatever that gravitational potential energy was at the end, it's the same as what it started with. And I can think of that as just subtracting out of the equation. I can subtract that same value from both sides and therefore, in effect, just cross them both out. So there we have it. The equation simplifies tremendously to the kinetic energy you end with is equal to the net work that was done by non-conservative forces. And as simple as this is, it's worth just commenting, don't forget that work is two things at the same time. Yeah, it's the act of a force through a distance, although we're not really focusing on that in this question, but it is the act of giving energy. In this case, the energy was given to that bullet in the form of kinetic energy. So Kinetic energy can be calculated as 1/2 mv squared, so putting the mass and the speed in will get us an answer of 225 joules. So to get that bullet moving, something had to do work to it, that something doing a total of 225 joules to give it that kinetic energy. Okay, number 2. A rope does 250 joules of work in dragging a mass along the floor. The rope makes a 30-degree angle to the horizontal and has a tension of 60 newtons in it. The question is, how far did the mass get dragged? Okay, so a little diagram will help. There's my generic box on the floor. I've indicated the force of tension, which is known to be 30 degrees above the horizontal. And of course, reading into the question, it's pretty safe to say that the floor is level. So this box is going to move in that horizontal direction. That's useful to realize because this 30 degrees can now be interpreted as that beta angle, the angle between the force and the motion. So I basically said the work done by the tension force is known to be 250 joules. That was given in the question. The force of tension is given as 60 newtons. That angle beta in the work equation is known to be 30 degrees, as I just discussed. We're looking for the distance that it moved. So pretty simple equation, especially if you list off in this given unknown format, that this is a nice application of the work equation itself. So the work done by any one force, for example, the tension force, is equal to the force of that particular force, the tension force, times the distance that it moved throughout that force pushing, multiplied by the cosine of the angle that pertains to that force. In this case, again, the tension force. So we know everything that we need to calculate the distance moved, so I just did the algebra here, solved for D, work done by tension divided by the force of tension cos beta, put the numbers in and got an answer. Moving on to number 3. Okay, this is a somewhat wordy question, and at first glance it might look complicated, but it's worth really thinking through what's happening because it can often tremendously simplify a question. In fact, if you know your stuff, you should be able to get the answer in your head almost as fast as you can read this question, especially combined with the circular motion unit that we just came out of. So in this question, there's a truck. I'm going to skip reading all the numbers here. It was a truck. It was moving in a circle. The road was level with a radius that was given. The question is how much work, just focus on this, how much work, right here, how much work does the force of friction do as it moves around some fraction of this curve? I don't even care that it's a quarter of the way around. That was really just a distraction, if anything else. Okay, so thinking about this, we know that if this object is moving in a circular path, especially this car on the road, we've actually seen that kind of a situation before, we know that the force of friction is providing that centripetal force to allow it to accelerate towards the center of the circle. So don't forget the physics that we've learned in the past. This is a situation we've seen before. So with the force of friction being directed towards the center and the velocity of that vehicle being directed along that circle, so tangent to the circle if you will, that tells me that the angle beta between the direction of the force and the direction of the motion is 90 degrees because this is towards the center and this is tangent to the circle. So that's 90 degrees. And just for the record, that's true throughout this whole movement. So if I were to consider the truck at some later point in time, just randomly choosing this point, don't forget that it would still be true that the force of friction would be towards the center of the circle and the velocity of the truck would still be tangent to the circle. So there's still a 90-degree angle between that force and the motion. So that remains true throughout the entire movement. That 90 degrees is essentially constant, even if the directions of the force and the direction of the velocity are changing. The angle between doesn't change. So as soon as I realize there's a 90-degree angle between my force and the motion, I realize that that force does no work of any kind. So the work done by the friction force is 0. And that actually makes sense because in this case, with friction merely steering that truck around the corner, it is really neither adding energy nor is it taking energy away. Now, of course, friction can do non-zero work, but in this case, it's not doing any work. From an energy perspective, the truck has the exact same energy at all points along the circle. In fact, primarily energy in the form of kinetic energy. And since it's not speeding up, it's not slowing down, that kinetic energy did not change as it curved through this quarter circle. So it didn't gain energy, it didn't lose energy. It's true that the work done by friction was 0. All right. Number 4. Okay, here's a question where you start to see the utility of this work and energy approach, because number 4 could be solved using the physics we've learned in previous chapters, like Newton's laws and kinematics. But in this question, especially, that this is going to be very, very, very simply solved using this newer idea, this work energy idea. Okay, so we know the model rocket is 4 kilograms. It sits at rest on the ground, and then it's basically launched upwards. There's an applied force of 250 newtons, which only pushes for a very short distance, a very short amount of time. It lifts at 8 meters, at which point the fuel runs out, but for the record, that rocket would be going fast. It would still continue to rise beyond that point. 8 meters is just the point that the applied force disappears. So the rocket continues to rise, and eventually it reaches the highest point before falling back down. We want to know what that maximum height reached. Okay, so to do this with Newton's laws and kinematics, you'd pretty much have to break this down into 2 parts. Part 1, the rocket is firing. Part 2, the rocket is no longer firing. And the reason you'd have to do that is because the acceleration of the rocket changes depending if the rocket is working or not working. Work energy is not even going to need to take that into account. Just have a look at this. Okay, so first of all, I'm going to use the ground level as that reference height. I'm going to measure height from the ground, which is a pretty intuitive thing to do here, I think. Here's a little visualization here. The rocket starts on the ground. It's not moving. Then there's this applied force of the rocket that pushes, but only for 8 meters, after which the applied force disappears. It continues to rise, slowing down, eventually stopping at some maximum height. So I've written the information down here in a kind of a, the given unknown equation kind of form. The mass is 4 kilograms. H that it started with is 0, so it started at ground level. The speed at that starting point was 0 because it wasn't yet moving. The applied force was 250 newtons. The distance that it applied through was only 8 meters, and the angle between the direction of the applied force and the motion was 0 degrees because the applied force was up and the movement was up. So that's why there's 0 degrees here. I want to know what maximum height it reaches. I'm going to call that h prime, at which point its speed will again be 0. This is really neat because the starting speed was 0 and the end speed is 0, although it's true that it wasn't 0 in between, which is fine. This is going to work out very nicely for us. Okay, so the total energy that it ends with, this is when it's at the maximum height, is going to be equal to the total energy it started with before the launch, plus the work that was done along the way by non-conservative forces. Now remember, I said that non-conservative forces in effect is all forces other than the force of gravity. So in this case, there is such a force, the applied force. And it is doing work because it's not perpendicular to the motion the way it was in the last question, the friction force was. So the applied force very much did do work here. Okay, expanding this out on the left side, mechanical energy, k prime plus u gravity prime. I've already crossed out the k prime because at the very highest point, it stops moving, so it has no kinetic energy at that highest point. On the right side, the mechanical energy it started with, k plus u gravity, I've crossed them both out because they're both equal to 0. It is k equal to 0 because it's not moving before it was launched, and u gravity was 0 for the reason that it was on the ground where height is 0. So on the right side, all that we have is the work done by non-conservative forces, which in this case is the applied force. That simplifies tremendously down to u gravity that you end up with is equal to the work done by the applied force. On the left side, we know that u gravity is mgh, so I've put in a prime there to denote that afterward value. And on the right side, the work done by the applied force can be found with f d cosine of beta. From here, it's just a matter of doing the algebra and putting the numbers in to get the answer. Okay, so to just finish off with number 5 here, which is actually a pretty straightforward question. We have information about a Big Mac, which is actually real information that I looked up from their website. We've got the mass of the Big Mac. We've got its energy content expressed in calories. So calories are not something that we're really officially making use of. That's why I gave the information that's needed inside the question. But it's true. A calorie, which I'm sure you've heard of before, It's worth knowing what that is. It is an energy unit, and it's equivalent to 4,184 joules. So in this question, just a quick hypothetical, if we could somehow convert all of that energy essentially into kinetic energy, that's what I meant by launching the Big Mac. We're going to get this Big Mac moving as quickly as we can, utilizing the 550 calories that it contains. So to solve this problem, we're just listing off the mass given in grams, rather, converting it into the equivalent in kilograms, 0.215 kilograms. We basically have the premise that its kinetic energy will be that value of 550 calories. Quick unit conversion here to re-express that as just over 2.3 million joules. As you can see, the calorie is a rather large energy unit compared to the joule, so 2.3 million joules in the Big Mac. And according to the question, we're giving that all to the kinetic energy of this 0.215 kilogram mass. So how fast would it have to be moving? Just a straightforward application of the kinetic energy equation, 1/2 mv squared, solving for speed, putting the values in, and getting the answer to finish off this problem set. All right, that should wrap it up for this video.